Ever wonder how something like ChatGPT actually works? Like, how does it understand what you're asking and come up with a coherent answer? Well, it's not magic. It's this brilliant piece of engineering called the transformer. And today, we're going to tear it down and see exactly what makes it tick.
Okay, so the very first hurdle, the big one, is that computers, they don't speak English. They speak math. They get numbers, not words. So step one for any AI is figuring out how to turn our language into their language. And that brings us right to part one. How in the world do you get from human text to computer-friendly numbers? Well, it happens in a couple of key stages. First, the model takes a sentence and just chops it up into smaller bits. This whole process is called tokenization. You can think of these little pieces, these tokens, as the basic building blocks, the vocabulary the AI is going to work with. Then, each of those tokens gets turned into a long list of numbers. It's basically a set of coordinates, like a point on a map, but a map with hundreds of dimensions. This is known as embedding.
Now, even this first step, tokenization, has gotten way smarter over time. The old way would look at bear and bears and think they were two totally different things, no connection. But the new way, subword tokenization, is much cleverer. It sees the root word bear and then sees the S as a separate thing, a plural. This is a huge deal because it's way more efficient and helps the model actually get the relationship between words.
So, once you have your tokens, how do you make them numbers? Well, the first attempt was kind of clunky. It was called one-hot encoding. Basically, imagine you have a dictionary with, say, 50,000 words. The number for bear would just be a list of 50,000 zeros with a single one in the spot for bear. Simple, but yeah, there's a problem.
And here's the massive flaw. With that method, the number for king and the number for queen are just as different from each other as the number for king and avocado. Mathematically, there's zero connection. This approach captures no meaning, no relationship between words at all. It's just a giant dumb list.
So the goal totally shifted. Instead of just assigning random spots on that giant list, the big idea became, what if we could learn the numbers? We could create these embeddings where the numbers actually mean something, where the distance between them shows their relationship. So now, in this new system, king and queen would be neighbors in this crazy multidimensional space, which makes so much more sense, right?
Okay, awesome. We've got meaningful numbers for words. Problem solved? Not quite. Because a word's meaning can completely change based on the words around it. And that throws us right into the next big problem, context. The first real swing at solving the context problem was something called a recurrent neural network, or an RNN for short. The idea was pretty intuitive. Let's read the sentence one word at a time, and with each new word, we'll carry along a little bit of memory of everything that came before it, like a chain. And what's wild is that the basic idea for this stuff has been around since the 80s. But as this quote explains, they just didn't have the horsepower back then. No internet-scale data, not enough computing power. The ideas were there, but the tech just couldn't keep up. Yeah, think of an RNN like you reading a sentence. You go word by word by word, and you're trying to keep a running tally in your head of what's going on. But, and this is the killer problem, its memory was terrible, like really bad. For a long sentence, by the time the RNN got to the end, it had totally forgotten what was said at the beginning. This was a huge, huge wall to hit. It just couldn't handle long-term context. All right, so if going one word at a time is too slow and forgetful, what's the answer? Well, the answer was something that wasn't just an improvement. It was a complete revolution. It was an idea called attention. The core of this revolution is something called self-attention. Here's the magic. When the model is looking at one single word, this mechanism lets it look at every other word in the entire sentence at the exact same time. It can instantly create direct connections between any two words and figure out which ones are most important for understanding the current word's true meaning.
I mean, this was a complete game changer. We went from that slow, one-by-one chain to processing the whole sentence at once, all in parallel. The model could see the entire picture, instantly. This didn't just make it smarter, it made it insanely faster to train.
And in 2017, a paper drops that changes everything. It's from a team at Google, and the title? The title tells you everything you need to know. Attention is all you need. That's it. They knew this one idea was the absolute key to unlocking it all.
So we've got our secret sauce, attention. Now, how do we build that into the full architecture? How do we assemble the transformer?
The transformer basically has two big parts that work together, the encoder and the decoder. Think of the encoder's job as reading and understanding. It takes in your sentence and uses self-attention to build this really rich, context-aware understanding of everything. Then, the decoder's job is to write. It generates the new text one word at a time, but it's constantly looking back, paying attention to what the encoder understood and also to what it's already written.
Okay, to really get how this attention thing works, I love this filing cabinet analogy. Let's say the model is looking at one specific word. It creates a query for that word. Think of the query as a question, like, hey, what other words in this sentence are important for understanding me? Now, at the same time, every other word in the sentence has two things. A key, which is like the label on a filing cabinet drawer, and a value, which is the actual information, the files inside that drawer. So what does the model do? It takes its query, its question, and compares it to all the keys, all the drawer labels. When it finds a key that's a really good match, it says, aha, and opens that drawer, pulling out the value inside. It does this for all the words, gives more importance to the best matches, and then blends all that information together. What you're left with is a perfect, custom-built mix of context for that single word.
All right, that brings us to the big finish. Why did this change everything? Why was the transformer the spark that lit the whole generative AI fire?
I mean, when you put them side by side, it's night and day.
The old way, RNNs, were slow because they had to go one by one, and they were super forgetful. The new way, with transformers, processes everything at once. This makes it blazingly fast and lets it scale up to huge sizes. And because of self-attention, it has a perfect memory. Every word has a direct line to every other word. No more forgetting. And that combination, that speed, that scalability, and that perfect contextual understanding, that's what cracked the code. That's what finally allowed us to train these models on, well, basically the entire internet. And that is what gave us the large language models, the LLMs that we all know and use today.
So let's end on this. When you boil it all down, attention is just a really, really good way of finding the most important information in a huge pile of data. That idea completely changed how we do language. So the big question is, what happens when we apply a similar breakthrough to other fields? What could a new kind of attention do for things like discovering new medicines or creating robots that understand the world? That's the question that's driving the next chapter of AI.